Hi, hello, welcome to section number 7. Woof, 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 woof. Um, we have our QR attendance code, so if you can, just give it a scan. I'm excited about the question for this today's attendance thing, which is like, what has been your favorite class that you've taken in college, or if you're in high school, that's always interesting for me to see. I hate to say one of my favorite classes was Chem 27. That really that's a red flag for me, but that was true. Some announcements. So remember tonight, regrade requests are due for the exam. There's also quiz 7 that's due tonight. Then I have some announcements that are more kind of me focused. So in week 5, which is next week, every year I hold student meetings. So I set aside about 9 or 10 hours to meet with y'all and to just do little check-ins. The way it's going to work in terms of logistics is in the next couple days, you'll get an email from me with a Calendly link to sign up for a slot to meet. The meeting times will be 10-minute slots. If you need to sign up for more than one meeting, or slot, do it. But these are typically going to be pretty focused meetings where you're going to come in and be like, hi, I want to talk to you about this. It could be exam 1 performance. It could be a specific study strategy. It could be a specific topic. But we are making a game plan, kind of bouncing ideas off of each other and getting feedback. And it's typically pretty focused. You also, if you don't have a clear goal and you just want to touch base, that is also fine. I would love to touch base and have a little one-on-one meeting, just because we're at the point in the semester where a lot's going on, and also I don't interact with y'all one-on-one very much. So check-in is next week. The other thing that's related to that is when I send out the sign-up links, I will also give you a very, very rough projection of kind of grade-wise where I see you right now. And it's just based on your exam score and kind of engagement that I've seen and what I've seen in previous years. I will give you a range of based on your exam score, I'm seeing somewhere between B- and B+. And it could go above or below that depending on changes. But in terms of where exam 1 is, that's where I would see. Or I could say, I see you in the AA-, or I see you in the C to B range. So I'll give you some sort of range. And then I'm also going to be sending the students that I project in the kind of lower grade range the first signups, so that they can sign up for multiple slots if they want to, and also they prioritize this meeting with them when that matches up schedule-wise. Again, it's an unofficial grade update. It's not a real thing, but just kind of, I think it's helpful to have that information and to get feedback. The other thing is feedback for us. So next week, probably on Tuesday, we'll release it. There's going to be a mid-semester feedback form on Canvas, a little quiz. It's an anonymous survey, and it's just to kind of let us know how things are going, what is working, what is not working. And so we really do want to hear from you. And in the past, what we've done is there's been some sort of incentive where if the class, 85 or 90% of the class does the survey, then everyone gets a 3% bump on the exam or something. So we do try to do some small incentive. I haven't talked with Tim yet about the logistics of what that is, but if you fill it out, there will probably be some incentive. I also recognize I'd said, well, we'll add points to the exam. We ended up doing that to exam 1 anyway. So there was that, but again, we do care about your feedback. We will definitely be reading the feedback closely, and I will see kind of everything. But yeah, that's kind of the big things for next week. My images associated with this are you get a meeting, and you get a meeting. You all get meetings. And then here's some feedback on organic chemistry. But, yes. Are you formally in my section? Yeah. Send me an email. I'll send you a calendar. Yeah. Cool. Other questions about logistics? Okay. So, full disclosure, lecture 7 is my least favorite lecture of the class. It's the lecture that, to me, I feel has the least narrative to it. Lecture 6, really focused, of substitution elimination. It all culminates in the GFP system. There are story beats of the lecture. Whereas lecture 7's like hodgepodge central. It's like, okay, we're going to talk about carbocations, then we're going to talk about ethers and epoxides, and making alcohols leave. It's just kind of, there's not a good through line for this. And it's really because all of the reactions that you learn in lecture 7 are basically glorified SN1 and SN2. So, like, yeah, it's just not my favorite section. I also think that it is not the hardest lecture conceptually. Like, the reactions aren't too intense. There are definitely some things that we are going to want to touch base on. But what that means is I'm probably going to spend like 50 to 60 minutes here. And then I want to spend the last like 30 to 40 minutes here. And this is going to be focused on, do y'all remember like my TED Talk in section 3 of how to study reactions, of like understanding it and going through all the like summarizing, whatever. So it's part of a trilogy. There's part 2 and part 3. Part 2 happens today. Part 3 happens next Friday, where we're just going to talk about some more study strategies for reactions. Then I want to do challenge problem 10 with y'all. It is the last synthesis on the problem set, and it's the hardest one that you've seen so far. And so I want to do that as a group just so you can kind of see what the game is now that we have more reactions. And yeah, I definitely will do this. The thing I would like to do is this extra challenge problem up here, where it's substitution elimination practice, and it's very, very similar to what the first page of exam 2 will look like in terms of structure. Sorry? I mean, pretty much. They're all like variants of substitutions, really. SN1, SN2. If I count or lie, I'll let you know.
No, just because I struggle to understand if I do S1 or S2, like when the reactions from S3 or S4.
Yeah.
When do you know?
We'll get to it.
Thank you.
Yeah. Okay. Any like logistical questions before we jump in? Oh, I should give you warning. So I've done something unhinged, which is, do you remember how I was talking about like transitions between the section like components of like, I always feel like I have to make a hard transition. I was like, I should get like the audio sounds to like play at the transitions, like a little TV show or a sitcom. So I've gotten 30 transition audio clips, and so we are gonna transition. That's a Raven. But I do have 6 Hannah Montanas. Like, the Hannah Montanas are, carbocation rearrangements. So, you'll recall from the last lecture and section that the more substituted a carbocation is from primary, secondary, tertiary, the more stable it is. And then, what's even more stable than a tertiary carbocation? A resonance stable carbocation. So if you have a carbocation that can engage in resonance, that's even more stable. So our new idea here with carbocation rearrangement is if you can form a more stable molecule, you will. And like molecules will actually do kind of really crazy things. We're going to teach you some basic rearrangements, but this is a really pervasive idea of like you always seek stability. Oh, that's kind of like a deep thought. I don't know. But so let's look at this. So in this molecule right here, we have a secondary carbocation, and we are adjacent to a tertiary carbon. When we are in that scenario, the hydrogen on the tertiary carbon can do a little scooch. And we call it a 1,2 hydride shift because the hydrogen is moving with its electrons. And so the hydrogen moves over here, and then our carbocation is now on that tertiary carbon. So we have a tertiary carbocation. Did we form a more stable carbocation? Yeah, so that's why we did it. We could form a more stable carbocation. Then, if you have a secondary carbocation adjacent to a quaternary carbon, so this carbon is 1, 2, 3, 4 quaternary, then you can have a whole methyl group shift over. And we would call this a 1,2 methyl shift. And then you form, yet again, a tertiary carbocation. Is it more stable? Yes. Yeah, of these. Mm-hmm. So if you, with these specifically, you're going from secondary to tertiary. Yeah. So, you're bopping around Cambridge. You're not going to just walk into the road without looking both ways, right? Like, you value your life. Value the life of a carbocation. If you form a carbocation, you need to look both ways before you react with that carbocation and make sure there is not going to be a rearrangement that could make something more stable. And I do have a little meme for her of like, this is you walking into a reaction with a carbocation when you forget to check for a rearrangement. This was me on the quiz when I tested out the quiz 7. I missed a rearrangement. I was like, wow, I feel like this. So always watch out for it. I didn't have time to put it on the soundboard, but I do have another audio clip, which is, these are kind of the basic ones that we teach you, but then there are much weirder carbocations that can happen. Like these are 1-2 shifts because they're going right next door. There are like 1-7 sigmatropic rearrangements where things are going over 7 atoms. Crazy, crazy, crazy stuff happens. We're not going to get super crazy, but we are going to encounter some carbocations that are a bit stranger. Stranger rearrangements, Stranger Things themes. There are going to be a lot of sound cues today, so just be prepared. Cool. So I've pulled some select practice from the problem set that are a little weird, and we're going to do them together. We're going to talk about them. This is the only reaction today I'm going to talk about with an alkene, and it's because alkenes are the focus of lecture 8, and it will be all of what we do in section 8. So this is the only reaction we'll see with an alkene. But what this reaction does is if we have an alkene and HBr, the carbon-carbon double bond will go and grab the hydrogen, and then we have 2 options. Option 1, we place our carbocation here and our hydrogen on the end. Option 2, we place our hydrogen here and carbocation on the end. My question for you, and show on your hands, 1 or 2, which of these is more stable for the carbocation? Work. 1 is more stable. And it's because this is a secondary carbocation versus a primary carbocation. So this is the only one that is formed. Okay. So we would get a product that looks like, actually I'll write it over here. This plus and a hydrogen over here. So now we're talking about rearrangements. What type of carbocation do we have here? Secondary, I'd already started writing it. Could we do a rearrangement to make a more stable carbocation? We could, right? So we're next to, what is this? Primary, secondary, tertiary, quaternary. Quaternary. And so secondary next to a quaternary, we would expect like a methyl shift. And I'll do this, actually. And so then our positive charge would be where we just moved the methyl. And then we could expect our Br minus to come in and fill the positive charge. And we would get this product. Cool. That's totally a reasonable thing to think of what would happen based on what we taught you. And this could happen, certainly. Now, one thing that won't happen is we would not at all get any of this product. This is the product where what if our Br minus just attacked here and we didn't do a rearrangement? We're always going to rearrange if we can, because rearrangements are intramolecular, they're super fast. And so if we were trying to get this one that I put over here in the brackets, we would be out of luck. So that would not be formed at all. So does this seem reasonable, like what you've seen so far? Like I kind of get like, cool. Let me show you something new. So we have talked very briefly in the past about this idea of ring strain. So like if you had something like a cyclobutane here, this is a 90-degree angle, that bond angle wants to be 109.5. And so this ring is under some strain. And a 5-membered ring is less strained, but still strained, And our platonic ideal is 6-membered rings. 6-membered rings are super stable. Everyone can be their bond angle that they want. So, if we have a carbocation adjacent to a ring that has ring strain, what we are going to do is a type of shift that expands the ring. So, I'm going to do this in green over here. We're going to take this carbon-carbon bond and have it move over. And we would call it a 1,2 alkyl shift. And this is a ring expansion. Now, when we're doing stuff with rings, it gets complicated and it gets hard to draw products well and things look wonky. And so my favorite tool for doing something like this is numbering carbons. So I'm going to number everything that's going to be in this ring. I'm going to start where the carbocation was initially. 1, 2, 3, 4, 5, 6. And so now I see that initially I had a 2-6 bond. Like 2 and 6 were bonded here. But then I'm taking 6 with its electrons and bonding it to 1. So 2-6 is going to become a 1-6 bond. So if I know I'm forming a 6-membered ring, I can just draw the cyclohexane here. And then I can just start to assign my numbers. So I could do like 1, 2, 3, 4, 5, 6, and then start to deal with all the other things that were attached to the ring that I didn't number. So like, what else is on carbon 1 that's not one of the numbered carbons? We have a methyl. So I need to make sure I have a methyl here. Then carbon 2, what else does it have? It also has a methyl. Okay, so we have all our atoms now. And then where did our carbocation go? And to answer that, think about who was robbed of a bond. Who had a bond before and now a bond has been taken away? 2. 2 was in this bond with 6, and then 6 took its electrons and bonded with 1. So we have a positive charge on 2. So now we have a tertiary carbocation, right? That's more stable. And in addition to it being tertiary, we've alleviated ring strain. And so can you see how this is an even better structure than this one in terms of stability? They're both tertiary carbocations, but one has less ring strain.
So then doing a lot of actually that, like the one that we just did.
Yeah. And this is something that we would typically test more in a mechanism question because you're having to think more mechanistically. In like line reactions, we would typically give you ones that are a little bit more straightforward. Cool. So here, the Br minus would just attack, and then we would be done. So the answer key, like the product that you're going to get, is this. With what hydrogen? This? I mean, she's there. I just implied her. Yeah. Cool. So given that information that you had, I want you to try to do a rearrangement here. So we have a strained ring next to a carbocation. So try drawing the arrow for the ring expansion and then drawing what it's going to look like afterwards. And just take a minute.
In mechanism, we have to know that 1, 2 are the first.
You don't have to. It's nice. Like it tells the grader that you know what's going on, but it's not necessary. So, do the rearrangement. And then here, which number, based on how I've numbered it, would have the carbocation? 2. We rubbed 2 again of a bond. And so what type of carbocation did we have before? Secondary. And what do we have now? So our carbocation is not more stable, but our molecule is more stable. Okay. And then could we do any other rearrangements? We have a secondary next to a tertiary carbon. So if we look up here, secondary carbocation next to a tertiary carbon, we do a hydride shift. So again, this part, the thing that makes it weird is you're just doing two shifts. Cool. Next one that I want to talk about is from challenge problem 6. And it is one that's happening in the middle of the challenge problem. And it's one where I'm going to tell you what the shift is. And the thing that I want us to practice is a drawing skill. So you being like, why does this happen? The reason is there's a product that you are given where you will see 2 different size rings. So this is the shift that's going to happen, and we're going to try to draw it. That's kind of the big thing I want to do. And this is a kind of weird structure. So this is what we would call a bridged ring. And here, it's made up of this ring, which is a 6-membered ring. You'll kind of see like a weird chair-like thing there with the 6 carbons. But then, it also has another 6-membered ring, bridged kind of together. So we don't do a ton of work with bridge chairs in this class. It's really more of a chemistry major thing. But in the product, we know that there's going to be a 6-membered ring and a 5-membered ring. So that's how we would have determined that this kind of rearrangement had to happen. But we are going to use that numbering skill to help us draw it. So 1, 2, 3, 4, 5, 6 for this first ring. And when I did this rearrangement, did I change any of the bonds inside that ring? With this curved arrow, did I affect any of the bonds inside that first ring? No. So I know I'm just going to have a straight up 6-membered ring like this. And then I can just number 1, 2, 3, 4, 5, 6. And it's arbitrary how I'm numbering here. Yeah.
For the other one, I was just like, why are you not telling me?
So it's because there's no way that you could shift to make it a 6-carbon ring. Like over here, you could expand because the carbocation's outside the ring. But once the carbocation's inside the ring, you can't expand the ring more.
So we could have just moved the bond to the end of it to start with.
To here?
So you can only move a bond to where the carbocation is, like we can put it at the member, like at the carbon group.
Here?
Yeah.
Yeah, no, because that's a primary carbocation, so like it's too high energy, it just wouldn't form.
So only with the
Yeah. Like you can only make more stable structures when you do a rearrangement. Okay, so we have this, and then I'm going to keep numbering 7, 8, 9. So initially we had a bond between 2 and 9, and then after the rearrangement we had a bond between 1 and 9. So let me keep going around here. I know that 6 needs to be connected to 7, then 8, then 9, and 9 connected to 1. And so with that, we can get all the carbons on. And this is like a really hard visual skill to go from something that looks like that to something that looks like this. That's why numbering your carbons is really helpful. And this is a strategy that's going to come back for radical chemistry in lecture 9, where you will essentially have to do this. Like it's going to get so kind of in the weeds. And so again, I just wanted to plant the seed now. So where would our carbocation be? Who did we rob of a bond? 2, man. 2 is getting the short end of the stick today. So here, what type of carbocation is that? Cool. Is that our most stable carbocation? No. We are next to a tertiary carbon, so what can we do? Exactly. So, bum bum, ba-da-ba-da-ba-bum. Carbocation rearrangement. Woo! And then this will go on and do things. I think it does like an SN1 and an E1, but you will see this at some point in the problem set. The last one is weird, and it's challenge problem 3. In challenge problem 3, the whole thing relies on one sentence in the instructions, and if you don't read the sentence, you wouldn't be able to answer it. So I've reproduced the sentence for your convenience. This carbocationic shift is observed to occur simultaneously with the departure of the leaving group. So let's kind of translate that. Basically what this is saying is, instead of leaving group leaving, forming a carbocation, then a rearrangement, it's saying the rearrangement and the leaving group leaving happen at the same time. So that's not something that you could have been expected to know. We had to tell you in the question. So based on this story material, this product, what has left? Yeah. Kind of similar in concept, but like there's no lone pair. Yeah. So what has left? This N2 down here. So we know our mechanism is going to have to do that. Like that's going to be the leaving group leaving. But we need a shift to occur. So maybe let's try to start mapping carbons onto each other. Well, this carbonyl carbon over here looks interesting in the product. Would you buy it if I said it was this carbon, the one that has the O on it already? Like that seems pretty plausible. We could also like skip one and we see we're at the bridge. Skip one, we're at the bridge. So that seems right. What looks like something has shifted? The methyl. So here, the methyl is not on the green carbon anymore. Where's the methyl? Down one. Exactly. So here, we know that this is doing an alkyl shift, a 1,2-methyl shift here. It moves down. And I don't want to get too in the weeds on it, but I do want to give you a quick like MO picture of what's happening. So we know that if we are kicking off this leaving group, we're breaking a bond. So what orbital is accepting electrons? The sigma star here, the antibonding orbital. So this is our sigma star, Cn. And our donor orbital is our sigma, Cc. And so what do you notice about the 3D orientation of these two orbitals? Like, how do they look relative to each other? They're parallel, right? And so the orientation of this has made it really easy for the electrons to move over. This is just like what we saw with E2 in the anti-periplanar orientation, where we wanted our antibonding orbital to be really lined up with that sigma bond to make the reaction as easy as possible. And this type of stereochemistry, you are going to see more and more when you get to Chem 27. So again, just wanted to flag it here. Cool. So let's draw what the product looks like. We have chair 1, chair 2. We would have the OH, and then when it first comes over, that CH3 is going to be directly up, right? Like based on this kind of like, it just flows over. But then this molecule also had a hydrogen here, right? Does this look right for this position on the chair? Is that an axial up carbon down here? No, it's equatorial up. So for the instant it reacts, it would look like this. But then what's going to do is it's going to rotate down and be in the normal chair structure. So when that happens, the CH3 is going to be this up equatorial, and then the hydrogen is going to be rotated down. Like the rotation part? So it's more so this CH3 is on the top of the molecule. And so if you would put the CH3 down here, it would have had to do like a, I was about to say a wagon wheel Watusi, something to like just jump barrel roll over the molecule, and it didn't do that. It's still going to be on the kind of top face of the molecule. And that is something that you can see here with it being on a wedge. So there are some context clues to get it, but like I was just kind of trying to explain why it looks like this. Yep.
Would the alcohol still stay equatorial down, or would it?
I was just about to get there. So where did our carbocation go? Yeah, our carbocation's here. So what's the hybridization of that carbon? sp2, we have an empty p orbital. So if it's sp2, it's planar. And so this is neither equatorial nor axial. This is like trigonal planar right here, and that's why it looks kind of wonky. Okay. Now, is this a stable carbocation? Oh, what type of carbocation is it? Secondary. Does anyone else have any commentary about this carbocation? In this case, it wouldn't be a lone pair push, but you're right to be thinking about the lone pair here. Resonance. Whenever you're in doubt for something happening, 9 times out of 10 for this class, it's resonance. We have a resonance structure here. Boop. Oh wow, I drew a really small chair. And our resonance structure has this CO double bond, and here everything has a complete octet. Now this isn't a lone pair push because we didn't kick anything off, and the only thing that was moving was electrons and p orbitals. So this is just a resonance structure, and it's our most stable resonance structure. So to get to the product, the only thing that we need to do is deprotonate, so something in the solvent. So this is how we're going to build on that skill of carbocation rearrangements, where again, our guiding principle the whole time is we will form more stable molecules if we can. And then sometimes weirder shifts can happen where we would have to give you some context clues, like we would have to give you a product and you might need to use your numbering of carbons. Bless you. Okay. Questions on this? Cool. So making alcohols leave. I really feel unhinged at a just new level, and I'm so excited. So the problem is alcohols are bad leaving groups. And so I'm going to first present a half-baked solution to that problem. So the half-baked solution is throw the alcohol in a vat of acid, strong acid. And let's see what happens. So if we start off with a tertiary alcohol and we put in a strong acid, we would protonate it, it would become OH2+, and it's tertiary, and OH2+ is now a good leaving group. Leaving group would leave, it would form a carbocation, and then the other like halogen from HBr, it would be Br, HI, it would be I, could go in and attack, and then we have an alkyl halide. So now it's a better leaving group. Okay, that's fine. This is SN1, and we can do it because it's tertiary. If we have a primary alcohol, we could protonate it again, make it OH2+, and then do an SN2 attack and kick off OH2, or an alkyl halide. So that's fine. We can do SN1 or SN2 or strong acid. Without looking 1 inch down at the paper, why is this not the best solution? What are some issues with it? And the answer is on the page, but try to think. I see people looking at the page.
Nobody looks on the
I know. Okay. So, tertiary alcohols, primary alcohols, who's missing? Why are secondary alcohols not a good choice with these strategies? Exactly. So tertiary, we're good for SN1. Primary, we're good for SN2. Secondary, we're kind of mad at everything. So, one, it doesn't handle secondaries very well. The second thing is, these are kind of intense reaction conditions. So imagine we had a molecule where we want to get rid of the alcohol, but also on that molecule we had a carboxylic acid and a nitrile, and we had an amine. Do you think that this acid might cause some other reactions to happen that we don't want to happen? Yeah, even if we couldn't name all of them right now. The idea that we are subjecting functional groups to strong acids, that's probably going to do some sort of reaction. So that's why it's not favored, and it's a bit more reckless. You will use these. They will show up on problem sets. You are very allowed to use it on like exam like questions if you use it correctly. But this should not be the first place your mind goes when you think about making alcohols leave. The first place your mind should go are this little family of reactions. So we have 3 options here for making alcohols into better leaving groups. We can turn this OH into a tosylate, and here's the abbreviated structure for tosyl chloride. Here, the mechanism is kind of you attack the sulfur, kick off a chlorine, and then deprotonate, and then you're just here. And one of the big things to pay attention to with this whole family of reactions is what happened to the stereochemistry of the carbon that we started with. So in this reaction with the tosyl chloride, we don't do an SN2 step here. Like nothing attacks that carbon and does inversion of stereochemistry. And so we overall just have retention of the stereochemistry. Is that okay? Okay. The other thing to point out is this O is the same O right here. We did not change that O, it just went and attacked something. Now the other 2 options, what we are doing is we are getting this oxygen entangled with the sulfur or bromine, and then the thing that we want to add, the halogen, is going to come and do an SN2 attack and kick it off. So in both of these examples, we've done an SN2 reaction at that carbon, and so we get inversion of the stereochemistry. So it goes from a wedge to a dash. So that's kind of why we have different flavors of this. It's do we want to retain or do we want to invert? And then sometimes we might just want a chlorine over a bromine, just depending on the molecule we're trying to make. But let's try this practice here where you're going to have to think through some of the stereochemistry. So this is a variant of page 14 in the problem set, and I tried to make it a little bit harder. And actually, am I going to do it? Yeah, no. Part of me wants to make it even harder, and I keep thinking like this is too easy. But just try it out, see what happens. Pay attention to whether the reagents are going to be inverting or retaining, what the product is. And then for these, where you have the product, you're going to have to predict what the nucleophile was that got this. And it would be a nucleophile for an SN2 reaction. So take a couple minutes, please chat with each other. 20 more seconds. Let's see how it went. Oh. Okay. So, SOCl2 pyridine, did we do an SN2? The SOCl2 reaction, does it has an SN2 step? Can I get a verbal? Thank you. SN2. So that means we're going to invert our stereochemistry. So that's going to take an OH to a Cl, and then should it be on a wedge or a dash? Dash, because we're inverting. Okay, then KCN is doing another SN2. And in fact, all of these for the second step is going to be an SN2. So over here, we know our final answer with the CN should be on a wedge. Okay. Now over here, we have N3 in the product. So what is our nucleophile version of N3? What should we put on the arrow? Mm-hmm. We have turned the alcohol into a good leaving group. The good leaving group has been formed.
I was like, nothing is clicking.
No, you're good. Yeah, so N3 we definitely need to have. And then it's probably going to be N3 minus to be a good nucleophile and be charged. And so we're going to cover up the minus with an Na. So NaN3. Okay, so this is doing SN2. So the thing before it should be on a wedge or a dash. Dash, because we did an SN2, we need to invert it. Okay. Oh, and that's not an N2 anymore. We need some sort of leaving group. So some leaving group. And we started off with an alcohol on a wedge. So whatever we do to make it into a good leaving group, it needs to be an inverting one. So what are our options? Yeah, we could do either chlorine or bromine version. We already did chlorine up here, so I'm just going to do bromine, but both would work. So here it's PBr3. One kind of like mnemonic is, I think PBR is a type of beer. I'm not a beer person. But that's what you want.
Oh, wait,
Yeah. But PBR in terms of like alcohol, PBR, that's a way to remember it. No, those are pretty much equal. But like, let's say your product has a BR in it, then you want to use the one with the BR. So it's just, those are roughly equal. Okay, and then the bottom one, so we had SH in the product, so how do we get a nucleophile version of that? What did we do for N3? Yeah, we just added an Na in front of it, so NaSH, NaSH. And it's not deeper than that. Like, I know that these reagents feel a little bit new because like this is not something that we're like explicitly teaching you. But does it seem plausible that it's really whatever this is with a negative charge, and we put an ion in front of it because we're writing as a reagent?
Any rules that you know about what ions we can use?
Not really. Yeah. For SN2, you typically just use negatively charged things. So yeah. So if it's on wedge for the SH, then what should our leaving group be on before? Dash. Okay, so we need to make a leaving group on a dash, and our OH started on a dash. So which one do we have to use? Tosylation, TSCl, with pyridine. Because that is not going to invert the stereochemistry. So at a kind of more like macro level, if we zoom out a little bit, we were trying to get this alcohol leaving and putting in some good nucleophile. And overall, this two-step transformation can either be retaining, so we start on a wedge, we end on a wedge, or it could be inverting, like this bottom one. But the weird thing is, the retention that you see in like this first one is 2 SN2s. So we call that a double inversion. And if we invert something and then invert back, we're kind of back to the stereochemistry that we started at. So it's just the idea that double inversion is the same as retention for stereochemistry. And what's that? We've stumbled upon a wild synthesis strategy. Oh my goodness. So if we started an alcohol and we wanted to either make the cyanide on a wedge or a dash, we could choose what leaving group we want to make that is going to help us either do one SN2 reaction and be overall inverting, or two SN2 reactions and being overall retaining for the stereochemistry. Again, I told you the sound cues really exploded this section. There were a few before, but this is just another level. And there was a big dramatic reveal. There was a box. Questions on this? Does this make sense as to, like, if we do two SN2s, we're going to get the same stereochemistry as we started with. If we do one, it's going to be flipped. Yep.
Why does the CL substitute?
Like, why does the CL just not come in and attack? I think it's because it's not a strong enough nucleophile to do that, and this isn't as good of a leaving group to do that. Over here, the CL can do it because this, you're going to kick off SO2, which is a gas, and she is excellent. Actually, thanks for asking about this, because whenever we can kick off a gas, it's going to be such a strong driving force for a reaction. Do you all remember Le Chatelier's principle from Gen Chem? So let's say we had a product here and we decrease the concentration of the product. Would that shift the reaction left or right? Right, because it's going to try to compensate for that. So when we form a gas, the gas is going to bubble off out of the reaction flask, and it's like we're removing a product, and it's going to keep driving the reaction forward by Le Chatelier's principle. And so this is a case where, even though chlorine is not the best nucleophile, this is going to be driven forward by Le Chatelier so strongly, whereas this, you don't have that same gas kind of release. Yeah, good question. It is. But it's all a balance of nucleophile strength and leaving group ability. And that's a more nuanced thing than really what we are like asking you to do. Yeah, but good thoughts on it. So I want to do a kind of non sequitur where this is kind of left field. Challenge problem 4. It looks kind of like this PBR3. And so let's see what we can emulate from the PBR3 mechanism to try to figure this out and maybe knock out part of a challenge problem. So in the PBR3 mechanism, what happens is our OH attacks phosphorus, kicks off a bromine. Then we are at this intermediate, and then the bromine comes and kicks off, and this thing leaves. And again, the thing that's going to flag that we're going to do something similar to this is just the fact that we are working with phosphates, and phosphate chemistry is kind of a rare thing for y'all to work with. So let's look at this. We have an alcohol, we have a phosphorus thing, a phosphate-ish thing. And then what do we have here? We have an alkene. What reactions do we know that make alkenes? E1 and E2 elimination. Good. So at some point we'll need to do that. And then what do you notice that's different about these two phosphorus structures? Yeah, so you've lost a Cl. So here there were 3 Cls, and here there are only 2. And you've added an O. So with those kind of goals in mind, let's try to do some arrow pushing. So what do you think a good first step would be based on the PBR reaction first step? Yeah, great. So we attack the phosphorus, the sigma star phosphorus Cl, kick off the Cl.
Why is that more favorable than
Because phosphorus oxygen double bonds are not like carbonyls. They have a kind of different structure, and that's why I'm wanting to do this here, because I think a lot of people on their own, if they were just starting it, they would try to attack it like a carbonyl. Yeah. So we have O, P double bond O, Cl, Cl, and we have a hydrogen here. And then I'm just kind of looking at this oxygen here versus the product. I see in the product it doesn't have a hydrogen on it, so I'm just going to deprotonate here. There are a couple spots that you could deprotonate in this mechanism and it would be fine, but I'm just going to do it here because making a more neutral intermediate. Yeah.
The CL that left, could it be, is what I always thought that it would bind to the H, and it's take the H first, then the pyrite will immediately react with the H.
I mean, it's a thing of like, when pyruvate is your solvent, you have moles of it. And then when you've kicked off a chlorine, you have one chlorine. And so, like, the chlorine is around, so proximity, but also pyruvate, it just outnumbers it. And so the identity of it doesn't matter, and that's the whole thing that, like, why we sometimes just use Sol. Because we don't care. Like, both. Yes. The answer to your question is yes. Yeah. So it's neutral. Okay, well, it looks like we are pretty much here. And it's almost like she just left, right? And so we can imagine this is probably a pretty good leaving group if she truly left. Okay, we need to make a double bond. So what mechanism-wise should we think about doing? So I'm hearing two options. One is like E1, where a leaving group could just leave on its own. And then 2 would be doing like an E2 situation. I will tell you a pyridine is a pretty good base. Yeah. And so because we're in a pretty good base, that's also why I use pyridine over here, because it's a better base than Cl. We are going to do a beta deprotonation. That's going to kick in, form a double bond, kick off, and we're out of products. And so this is one that like looks intimidating and is not chemistry you've directly seen, but the steps of this are very similar to things that you have seen. Cool. Questions on this?
So I think I'm just gonna take a break.
You're getting really excited to hit that play button.
Ham.
Um,
You saw me reaching. Well, it's because I'm going to do one of Hannah Montana's. Let's talk about ethers. So, I'm going to start off teaching you a tool that's helpful for me, but is truly a me thing. It's not like everyone in the world does this. So, not all ethers are the same in terms of the types of carbons that are attached to it. So one really helpful tool for me personally when working with ethers is to classify both sides of the ether as either primary, secondary, or tertiary. So like this carbon here is attached to one other carbon, so it's a primary, whereas the carbon on the other side is attached to 2 carbons, so it's secondary. So I would describe this as a 1' plus 2' ether. Okay, what's the left part in this next one? Primary, secondary, or tertiary? Tertiary. So this would be a 3' plus 2'. And can you fill out the rest real quick? Cool. So you are going to see why this is important in a minute, but I just want to introduce that nomenclature. So, whenever you are trying to build an ether, the first thing that should come to your mind is the Williamson ether synthesis. This is the most important reaction probably in the whole lecture. Like it is going to be used on synthesis, box problems. It's such a standard reaction for making an ether, and I want to prioritize that this is better than all the others, generally speaking. It's going to be the most common one. Williamson ether synthesis is like the prototypical way of doing it. So what you can do is you can start off with what I'm calling an any prime alcohol. And again, this is a me notation, but it just means this alcohol could be primary, secondary, tertiary, we do not care. So start off with some alcohol. Step 1, you add NaH, the base. And you always use NaH for Williamson ether. When you add the base, you're going to deprotonate it, and it forms an alkoxide. And then in step 2, this alkoxide is going to do an SN2 attack of an alkyl halide. So what we get out of it is our oxygen has attacked that carbon on the alkyl halide, and we've made our ether through this SN2 mechanism. And so this is a really great strategy for making a ether that is 1' on one side and then any prime on the other side. So based on that, if we know that one side of it needs to be primary to do Williamson ether, which of these 4 options could we have made with Williamson ether? The first and third ones. Because here you have a 1' on this side, and so you could have done this one as the Br, and then the other side is the OH. Then over here, similarly, that side would be the Br, and the other one would be OH. So that's why this kind of classification system I think is helpful. Because when you can clock a primary somewhere, you know you can make it with Williamson ether. Alkoxide attacks. It's O-, it's the nucleophile. So this is our main option, but we have another way of making ethers, which is doing an SN1 mechanism. So if we have a tertiary alcohol, an acid, we can protonate it, leaving group leaves, and form a tertiary carbocation that's pretty stable. And then another alcohol that's any prime can go and attack. And so this can make ethers that are 3' on one side, any prime on the other. So based on that, which of these could we have made with SN1? 2 and 3, because these have the 3' parts. So again, that's why this analysis I think is important, because you're thinking in terms of SN1 and SN2. Now, we don't have a really great way of making secondary, because our choices are really SN1 and SN2. You can do some weird things with ethers. You can make cyclic ethers if they're both on the same molecule. And then you're going to learn 2 other ways to make ethers later on. So keep your eyes out for it, and if you spot a way of making an ether, say something. How to destroy an ether? It's basically the same 2 options of SN2 or SN1, but you have to use harsh reaction conditions, and there's just no way around it. It's because ethers are not very reactive, and so if we want to break up an ether, we have to kind of subject it to some intense conditions. I'm not going to really get into this. This is more for a reference for you to come back later to, because you rarely do this reaction of breaking ethers. But yeah, just the warning is secondaries are pretty hard. And you'll kind of explore some of that in the problem set. Cool. I'm going to move on to epoxides. I know I'm going quick, but I want to make sure we have time to chat about the synthesis and starting reactions. So now we come to one of my favorite functional groups, the epoxide. I just think they're cool. They're reactive. They're ready to explode. I also really like that epoxide, their government name is Oxirain. So like in IUPAC nomenclature, you would call this like Oxirain, or actually, I'm not good with the IUPAC for the hard parts. I have not done it in forever. But I know epoxides are Oxirain somehow, and then the other one that's kind of weird is like if you have a thioether, she's Mercapto. I'm like, huh, how did that happen? I don't know. But you know at this point one way of making epoxides, and that's from this functional group called a halohydrin. Can we say that together? Halohydrin. So halohydrin has a halogen, halo, and an OH, alcohol, hydrin. This is a compound functional group, and if you were to call this an alcohol and an alkyl halide, that would not be the best answer. So when you see one of these alone, check for the neighbors, see if something's nearby, because halohydrin is one of these new functional groups. So the way that it's going to make the epoxide is you're going to add a base, typically NaOH. It's going to deprotonate this, make this O-, and then it's just going to do this intramolecular SN2. So again, everything in this lecture is just repackaging SN1, SN2. You are going to learn another way to make epoxides in lecture 8, so be on the lookout for it, and it's one of my favorite reactions that you'll learn. So she's going to come back. Woo. So the big thing that we are concerned about with epoxides is how we open them. I did make a meme. I like put this into ChemDraw. So we talk about epoxide openings. And so here in this reaction, you're trying to crack open a cold one with the boys. No? Is it bad? Is it a bad joke? Cracking up on cold ones with the boys? It's fine. It's fine. But when we have a symmetric epoxide here, it doesn't really matter which side our nucleophile attacks because they're the same, right? But when we have a more complicated epoxide like this one, we are going to want to control whether or not we attack this more substituted side or our less substituted side. The way that we control which side a nucleophile attacks an epoxide has to do with acidity and basicity. So if we are an acid, our nucleophile will attack the more substituted side of the alkene. So for these two reactions over here, our nucleophile is in this dark red, and you'll see that it added at this top carbon for both of them. It added the more substituted side. The general reason for it has to do with like, when you're an acid, you protonate this epoxide, and it has to do with like partial positive stabilization on the more substituted side. That's a little hand wavy. We're not getting into a bunch of the details. But really, at the end of the day, you just need to know if I'm trying to open it at the more substituted side, I use acid. Here, like if you wanted to add an OR here, you would just use an alcohol and acid. If you wanted to add an OH, you would use H3O+. And the functional groups that we made here are two OHs next to each other, vicinodiol. And then we found one of our other ways of making an ether. Oh my gosh, came out of nowhere. So here, this is an ether right next door to an alcohol. Now, if we want to add on the less substituted side, we do it in base. And the reason is just it's faster. So here, our nucleophiles here are in the dark blue, and we see both of them add to the less substituted side. They add to this bottom carbon from the epoxide ring. And when our nucleophile adds on this bottom position, the oxygen that was in our epoxide is still there, and it just goes to the other carbon, or it stays on the other carbon, I should say. So the acid base, which side we attack, is the biggest idea here. I also want to briefly talk about the stereochemistry. So if our epoxide is on wedges like this, it's going above the ring. So this is kind of our epoxide in 3D. And when we are thinking about where to attack, we're attacking the antibonds for the CO bond. And so the antibonds are going to be down here below the ring. So far, does that make sense of if we are a nucleophile, we want to attack the antibond? If the epoxide's above the ring, we will have to attack from below the ring. Does that seem okay? Okay. So if we are attacking from below the ring, then when we look at our nucleophile, we would expect our nucleophile to be added on a dash. And that's what we see. In each one of these cases, our nucleophile, when it attacked from the bottom, so it's on a dash, it's below the ring. And so that's how you're going to be predicting the stereochemistry. The OHs on the other side of all of these came from the epoxide, which was on the wedge initially. So it does make sense that it stays on the wedge. Yes?
Like why season
Because it was just there. Like this, you still have this wedge bond, and so when a nucleophile attacks here, breaking that doesn't affect this being a wedge. Yeah. This is really meant mostly to be a reference image that kind of summarizes the things from lecture for y'all. And so we're not going to do a ton with it. I had a little exercise I'd like to do, but I'd much rather get to the stuff on the next page because I think it's going to be more important in terms of like regrouping. Are there any kind of final ether epoxide questions before we jump into the other stuff?
Like, well, I don't think I'm touching this like later in the last page, but also like there's so many reactions that we're doing, like how do we know which ones to use?
It depends on what you're trying to do. Like it all has to do with kind of functional group tagging and thinking about like options that you
Would it
have.
be, like, eventually, like, multiple ways to reach a final product then, or, like,
Potentially, yeah. Like we've had synthesis on exam before where there are two right ways to do it. There was a box problem that we had on the first exam for y'all, and the way we intended y'all to do it was not the way y'all did it, but y'all did it a correct way, so we added it to the answer key. Yeah. So yeah, there are often several ways to do it. Okay. What's the transition this time? So thanks for coming to part 2 of my TED Talk on how to study reactions. You all have done some studying of reactions at this point, and so you've tried out some methods. And one of the kind of big issues that I think a lot of students face when studying reactions is how can you study in a way that both is going to prepare you for exam type questions and the way that you're going to be tested, and is time effective? Like that's really kind of a golden combination. And so I want to show you a strategy that I like using that I call the die. You do dies. Organic chemistry makes me want to. But it's a short exercise here, and I'll kind of explain it. You start out with a blank page where you are going to write out the starting materials of a reaction you want to study exactly as it was presented in lecture. So I've done that here for you. I've drawn this aldehyde and this primary amine from lecture 5, and this is the amine formation reaction. And then you are putting all of your study materials away. So just blank page here. Oh, and I didn't explain the name, DIE, Desert Island Exercise. So have you all heard of taking an exam like in desert island conditions or doing practice like desert island kind of style? Wow, I really thought that was a much more common phrase, but I'm finding that no. Maybe it's just the millennial, Gen Z, zillennial. So like doing something under kind of desert island conditions would be doing it with nothing else, just you and your pencil. Of like there are no resources that you're looking up, you're not looking at an answer key, and it's trying to simulate the actual kind of exam conditions where you're going to be confronted with what you do and don't know. And so I like this idea that it kind of is this isolating feeling, and we are going to do that feeling for 3 minutes. So the exercise is, once you've written this out, you get a timer. Everyone take out your phones. We're actually going to do this. And prepare a 3-minute timer. Do not press start yet. If you are a student that's working on paper instead of a tablet, I would go ahead and write these out so that you have it before we try to start writing it. But then we are all going to press start at the same time, and we're going to try to go through this mechanism on our own. And the exercise is, in the 3 minutes, you are going to try to write what the product is and do that one first, and then try to write the mechanism to get there. So, are we clear on what we're doing? Does everyone like have this reaction up? Because I'm going to do the exercise too. Okay, I'll count down 3, 2, 1, and then we'll press start on go, okay? So 3, 2, 1, go. So, check me, check yourself. Go through and grade, see how you did. Ask questions, yeah.
We went to that a group project, when I did a transfer to proton from the end page twice. I did a proton transfer and
So, in total, in this reaction, to get from this to this, there are 3 protonation or deprotonation steps. A proton transfer can only be used to abbreviate 1 protonation, 1 deprotonation.
yeah, I did one, then I wrote the output and another.
So, but if you did 2 proton transfers, if you did a proton transfer after this, then you would be saying that 2 things would be moving. So did you go to like this minus? That would not form.
Well, isn't the
Yes. So that's the thing that I like. It's my preference. There are a few different ways that you can store the protonation states that are correct, but my preference is always to form this hemiaminal because it's the most stable. And so it's going to be the intermediate that you can isolate most readily, so I think it would be good to show it.
If you're at page 5, why would you be putting oxygen?
Because the pKa of a protonated carbonyl is -2. So, and also if you were acidic enough to protonate a carbonyl, then your amine would certainly be protonated and you wouldn't have a lone pair to attack. So that's why it has to be this kind of weird pH 5 condition.
Could you just think of it as like an ion reaction?
This is,
Like
this is the reaction, the amine formation reaction, yeah. So, after the 3 minutes, stop, like actually stop, do not keep working on it. But I really like having the 3 minutes to let yourself struggle with it and to kind of see what you do and do not know. Because if you were waiting to feel that until the exam, 1, that's very stressful. And then 2, you're not practicing for that. When you are doing this, you have the answer to this in your literal lecture notes. So you'll be able to grade it for each structure, each arrow, and grade it for accuracy, but more than that, grade it for timing. Like when you were drawing the product at the very beginning, if that took you 45 seconds, that is too long. You want to get for these reactions where you could probably draw the product in 10 to 15 seconds, which seems kind of intense, and as you are starting out, it will be intense. Let it be what it's going to be at the start, and then work through it and see how to make it faster. Like questions that you should be asking if there's a step that took you a minute to get through these protonations, you should ask yourself, okay, what are my goals? Well, I want to get to this hemiaminal that's neutral, and then I need to make sure this OH is fully protonated so that it can be kicked off as water. And like thinking about it that way kind of prompts you to ask questions on the mechanism for what isn't clear, and it lets you like practice it in real time. So I really like this. And after you do it once and like assess yourself and kind of reflect for a minute, do it again. Do another drill, get a blank page, same molecules, and do it until you can be pretty comfortable with this. Where you're like, I feel confident that I can get the right answer, and maybe I'm still working on time. This is phase 1, the basic reaction as we have taught it to you. Phase 2 is trying to generalize it. So the first step would be try it out with a different amine and a different ketone or aldehyde. Maybe make your carbonyl compound look a little weird. Maybe, if you want a challenge, do an intramolecular reaction. Like there are so many ways that you can vary it to make it harder for yourself. And in these, the hard part is really going to be the structure of the product because the curved arrows will be exactly the same. And you're going to want to just repeat this kind of exercise of trying this out with the reaction until you feel pretty confident on the reaction generally. Like this is a reaction that you know how to get the product pretty quickly. You could do the arrows. And I think that that is really going to help you get the basics down. Now, this is a exercise that tackles the skill of encoding reactions. Like how do you get the information or reaction into you to where you can reproduce it? This still is not addressing the retrieval of those reactions, of like how to spot that we're doing a certain reaction in a box problem or synthesis, which that's what we're going to talk about next week. But this, I think, is a really foundational skill, and it's a great exercise to help you work on it. Then you can do things like start with the products and then do the reverse reaction and kind of see what would come together to make it. Why I like this? Active learning. You are actively writing the whole time. I think it's better than flashcards where you're just having to see or verify something. The time constraint. I love it. I love it because it's 3 minutes. It's a fixed amount of time where you can't fixate on one reaction for half an hour. And so it kind of keeps you honest, and it keeps you in this process of kind of rigorous and honest, like, self-assessment that keeps you really focused while you're studying. Because you could do 10 of these, like, die exercises in a row, and that's 30 minutes of studying. Like, I mean, yes, it's a little bit more with the review, but it is something that could let you touch on a lot of reactions and study them and review them. Or if it's a reaction that you don't know as well, you could do the same exercise with that reaction several times and make it harder and build skill on one reaction. So that's this whole, like, flexibility. Like, you don't need to do 5 of these with every reaction if you can get the reaction in 1 or 2. The last is just pragmatism. Like, with something like flashcards, you're investing so much time making the study resource before you actually study it. And same with rewriting notes. Like, it's not active recall, you're kind of just copying down. And so just for all of these reasons, I really like this exercise for learning reactions. And so just something to try out while you're studying.
Would you recommend still like incorporating flashcards from the beginning, and then once you know the basic mechanism, then switch to doing it? Or would that take too long?
Potentially. Like, to me, if I was actually sitting down and trying to learn the reactions, what I would do is I would annotate my lecture notes with the sub-step logic, make sure I understand why each of the errors are happening, then I would jump into this exercise. Just because, like, it doesn't have the lag time of making a flashcard and then doing that for a bunch of flashcards and then doing the flashcards. But also, like, you know how much free time you have. Yep. Okay. Last thing that we're going to talk about is this synthesis. We have 8 minutes. To be fully honest and transparent, I will go 5 or 6 minutes over, but you will be done with the synthesis on the challenge problem if you want that. Feel free to leave beforehand. I will not be offended. This synthesis is a 10-step synthesis, and it's the hardest one that you've seen so far, which is why I kind of want to talk through it with y'all in terms of how to approach something like this that looks very scary, and also, like, to do this together as an exercise. So when we start off with a synthesis, what's the first thing that we should do? Functional group ID. So what functional group do we have in the left molecule? Yeah, and we don't really know any reactions with the arene ring, but I really like noting it just because it is a kind of glaring feature of a molecule. So, like, for example, do we have a benzene ring somewhere in our product? Cool, yeah. So it's the phenyl here. And based on that, like, let's say I'm going to call the carbon of that alcohol orange star. Do you think it's reasonable to assume that orange star is right here? The carbon right connected to the phenyl? So already we're starting to map things on, and we're using these kind of as benchmarks and things to kind of latch on to. So yes, we have an alcohol. And then what functional group do we have over here? You didn't fall for my trap. Anyone want to say what the name is? Halohydrin. So, again, it's not just an alcohol or an alkyl halide because these are right next door to each other. So you guys only know at this point one reaction with a halohydrin. So what is this going to form? It's going to form an epoxide. So let's go ahead and draw what that looks like. Okay. Ooh, I see a structural feature that's kind of popping out to me here. What do y'all see that's a structural feature of this? Yeah, we have 2 methyls on the same carbon. And that geminal dimethyl, hashtag Gemini. Do we see something in the product that looks like 2 methyls on the same carbon? These are probably the same. And so it's not a kind of like magic here. We are going through a like really methodical process of step by step, which means that this kind of green star carbon, the one that has the bromine, that's probably going to be the green star that's here in the product of the alkane. So piece by piece, we're starting. Now, functional groups in the product. An ether. And our ways of making ethers are what? What's the number one way of making an ether? Well, use some ether. And then what's the other way that we saw as it popped up on the next column? It's like, oh, surprise. Yeah, we can make an ether from epoxide. Cool. And then our other functional group, we have an alkene. And what type of reactions make an alkene? E1 or E2. So we know that probably making the ether or making the alkene is one of our last steps because those are the functional groups that are present. So let's imagine what this molecule would look like before we did an elimination and just see. So one option would be we would have some sort of leaving group here on the left carbon of where there was the alkane. And the other option would be having your leaving group here on the right. So do you see how both of these are options that we could then do an elimination and kick off the leaving group and get the alkene that we want? Okay. So again, percolating all these ideas. We've done some brainstorming on the product. Let's do some brainstorming on the starting material. So alcohol. Can someone tell me a family of reactions that you know an alcohol can do? Redox, sure. So we could take it to an aldehyde, we could take it to a carboxylic acid. What's another family of reactions? Well, alcohol, oh, okay, yeah, better leaving groups, I like that. So we could turn it into a bromine, a chlorine, or a tosyl. And then our other kind of alcohol things are kind of hodgepodgey. So like, we can make an ether, we could make acetal, we could make part of an ester, maybe. But this, we're kind of scraping the bottom of the barrel. Like, these are our main alcohol ones. I guess we could do an E1, but brainstorming. So let's kind of back up and see some big ideas and big goals of this reaction. I mean, one of the big things that I'm saying is we need to get these two molecules to come together, right? And specifically, we need to connect the green star and the orange star. So that's kind of one of our big things that we are trying to do in this reaction. And when we are doing a reaction trying to connect things, that means something needs to be our nucleophile and something needs to be our electrophile. Well, our green star over here, that is going to be in this epoxide because that's the only thing we really can make with it. And so is the epoxide a nucleophile or an electrophile? Electrophile. Okay. Well, let's see, can we make this orange star carbon into a nucleophile? So are any of these functional groups nucleophiles? If they were on the carbon? No, that's a leaving group. Yeah. None of these, really, are nucleophiles. So that means we would probably have to go here and then do something else. Okay? Well, if we look at this, this is not only just like a new bond formed. This is a carbon-carbon bond. And you guys, in this course, will learn very few reactions that create a carbon-carbon bond. So what are some reactions that y'all have seen so far that create carbon-carbon bonds or have carbon nucleophiles? A carbon as a nucleophile. What? Sure, Grignard. Because let's look at like a prototypical Grignard. Here, if you had like ketone aldehyde and you had MgBr, this is going and attacking the carbonyl. And what we've definitely made the O-, which will become an alcohol, but we have made a carbon-carbon bond here. And that and like C and minus doing an SN2 attack are right now the only ways you know of making a C single bond. So, okay, Grignard, we could also say like lithium. But if this is our electrophile, we want to make this carbon here, the orange star one, into a nucleophile, and maybe it's our Grignard. How could we go from an alcohol to a Grignard? BR, and can we take an OH to a BR? Yeah, okay. I think we're ready to like try putting some things together. So again, all of this was planning, but truly we couldn't really start without thinking through it. But this is why I'm saying that this is a different game, this type of synthesis versus the easier ones you've seen before. Okay, so let's start off making the epoxide. So we have our halohydrin, we want to make the epoxide. What reagents should we use? NaOH. And it's okay if you do not have that memorized right now. That was lecture yesterday. Would you at least know where to turn in section notes or lecture notes where you could find that reagent, even if you couldn't think of it off the top of your head? If the answer is no, let me know and I can like tell you like where you would go. You would be like, oh, okay, I'm going from a halohydrin into epoxide. Where was the part of section that talked about epoxides? Halohydrin to epoxide, use NaOH. Okay, and then we have our alcohol here. So our strategy is we want to go from our alcohol to a bromine to Grignard, MgBr. Well, exam 1 stuff, to make a Grignard, you would use magnesium diethyl ether. What reagent would we use to go from alcohol to a bromine? TBr3. Again, we would just go to making alcohols leave. We would see alcohol to bromine, PBr3.
How do we know to make reactant versus the other one?
Because we only know how to turn this into an epoxide, and epoxide's an electrophile.
So we can't treat the PR as like a positive thing.
Well, see, if you made a Grignard here, MgBr, this would react with the OH on another molecule, and it would just do a deprotonation. Because remember, Grignards are super basic. Yeah. Okay, so let's try to combine them. So we're going to do 1 combine with ether, and then 2 H plus Perca. So when we do this, we just said that Grignards are basic. And so which side of the epoxide are we going to attack? The more or the less substituted side for basic? The less. And is that what we want? Like our orange star is here, our green star is here. The green is the less substituted side, so whew, that's what we want. Okay. We didn't really check that and it just kind of happened to work out, but such is doing synthesis. So we've accomplished that big goal of making the green-orange bond. But now if I'm looking at this, like I could certainly turn this into an ether. That's no problem. But going from here to something with a leaving group there, that's tricky. Why is that tricky? Do we have any functional groups here? No, these are just alkanes. And so we don't know how to just install a leaving group out of nowhere. We have to have another functional group. So this is the point where we get our trumpets and we play taps and we do bum, 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 for a dead synthesis route. So this is not going to lead to our product. But we wouldn't have known that until we had gotten here. Like there wasn't a way to just intuit how to do it the other way. And again, when you're getting into 10 and 12-step synthesis, you likely are going to have at least one route that you have to follow just to eliminate something. I know it's a lot, but we can regroup. So the big kind of insight here that I'm going to kind of tell you because I've seen it a little bit more is when I saw these options, something occurred to me that probably did not occur to y'all. And that is, here, we have functional groups on neighbor carbons. Whenever I think of functional groups on neighboring carbons, immediately my head goes to epoxides. Because look at every single one of these products here. And each one of these, when we've reacted with epoxide, we have things going on two carbons right next to each other. So what that means to me is I think that we need to do some stuff with the epoxide before just attacking it with the Grignard. And we need to do something to introduce another functional group. Because right now, if we only attack it as is, then we are getting a single functional group. So what's a reaction that we could do with this that would maybe accomplish one of our goals here that we're trying to do, but would introduce another functional group? What else could we do with this epoxide other than just connect it to the orange?
Can we make another GPO functional group?
I mean, maybe, but again, that's the issue where we would have the two. We can open it. Open in how? Do what? Well, so the base attack we've already done, but why don't we try to do the ether? Just because we know that we will have to do an ether on that part of the molecule at some point. So let's try to do it. Okay, I'm going to do this in like purple. So if we want to interact with this side, the more substitute side, do we need to be an acid or base? Acid. Here, if we want to attack on the more substitute side, we use acid. And here, if we're trying to install an ether, we're going to use an alcohol and H+. So let's try it. We have H+, and we want OET for our ether, so we're going to use HOET for our alcohol. Okay, so that's going to install our OET where we want it. And then on the other carbon, we will have this OH, where this O came from the epoxide. Okay, well, we've accomplished our goal where now we have two functional groups. So hey, that's getting close. And then the other thing is we still need to connect the green and the like orange star somehow. And we have this good nucleophile. Now we need to think about how to make this into an electrophile. So how could we make an alcohol into an electrophile that a Grignard could attack? We could oxidize. And we've already done that brainstorming work over here. So we could look up here and be like, what's a good electrophile that a Grignard attacks? Well, it attacks ketones and aldehydes. Cool, so let's try it. So we are going to form OET aldehyde. And if we're doing oxidation, what reagent should we use? We should use chromium. That's our big oxidizer. Lithium anhydride is our big reduction. And then should we use pyridine or H2O if we want to stop at the aldehyde? Pyridine. Good. Okay, so now our green star is an electrophile again, and our orange star is a nucleophile. So I think that we are ready to try combining them. Take two. So I'm going to bring these two together now. I'm going to do one, combine, ET2O, 2, H+ workup. And now we're going to get something that looks really similar. Actually, I want to do a different color. Yeah. So it was dead because here, at this point, we don't have any functional groups, and we need to have some sort of leaving group in order to do an elimination. And so you can't really go from no functional groups to adding a leaving group. So what is on here that I'm missing? So we're attacking a carbonyl. So when we attack a carbonyl, what do we have functional group wise after? We're gonna push up, have an O minus that we protonate, and so it's gonna be an OH on here. And now this is that thing that I was spotting where we have two functional groups on adjacent carbons. So we have like 1 or 2 steps left and we are done. We are so close. We need to do an elimination, and we have an alcohol here right now. So what ideas do you have for what we could do to do an elimination? We could do an E2. So we could turn this, like OH, into a BR or something, and then we could add a base and eliminate. That totally works and would get full points. Is there a way that we could do it directly? Are there any eliminations that start with an alcohol? So this is an E1. What's the way that we can get only E1?
Oh, H2SO4.
We could use concentrated H2SO4. And that is going to protonate this, it leaves, and then we would do an elimination. So, there we can get it. Or again, we could totally do the bromine route where we have Br, OET, and then we could use like terpbutoxide, and we could get to the product. It's a lot. This is a very different game that we are playing than the ones for exam 1 that were 5 or 6. This is the synthesis that used a reaction from every lecture that you've been taught so far. This is the level of the synthesis on exam 2. It will not be harder than this, but you will have other reactions. But this process of like thinking on paper, brainstorming reactions, trying out a route and seeing it doesn't work, you can only do that thinking when you're not having to think a lot about how do I draw the product. When you're not having to think a lot about like the recall time of like looking up reagents. And so let that guide you for your studying of like how to get good at synthesis. You need to let your time for synthesis be on the thinking, not the what is the reagent, not the let me draw the product. I went way over. This is a lot, but thank you for coming. Thank you for staying. I hope this was helpful. I'll stick around to answer some questions. But I will see you all next week. I hope you have a good weekend. Thank you for coming.